been developing wastewater-based methodology for a while now, focusing not on those SARS-CoV-2 but also other agents, especially chemicals, various different chemicals. And I'll give you some examples about this today. So what is so special about wastewater-based epidemiology? So every day of our life we are exposed to various different agents, chemical, biological, some that we take on purpose, like lifestyle chemicals, pharmaceuticals, others like chemical toxicants we are exposed to unintentionally. And our bodies respond to this exposure in various different ways. These are usually endogenous processes such as metabolism-driven processes that leads to the formation of various different entities. And this can be metabolites, can be elevated levels of certain proteins, and can be actually also changes at genetic level. So when we look at the exposure effects, we can identify biomarkers of exposure and biomarkers of effects. And they all, if they are excreted with urine or feces, end up in our wastewater, especially in our wastewater treatment plants. So wastewater is a fingerprint of communities' health and lifestyle. And what we do, we collect wastewater samples across various different sites within our region when we live, and I will tell you a little bit about it in a second, but also nationally and internationally. There are some really nice international campaigns that we do on a regular basis. So why is wastewater-based methodology so special? It is comprehensive because it encompasses whole communities. So it provides us with the best possible overview of what's happening at the community level. It has its advantages. It cannot identify individuals, so we do not really know who has been exposed or who is ill. So wastewater-based methodology can be used more as an early warning system, indicating that something is happening in the community, and then if there is something happening, maybe some kind of individual testing needs to be implemented to identify where the problem really lies. So please remember, it's more of a kind of early warning system that can provide us with comprehensive information about communities' health, continuous information, because we can collect samples all the time, every day, and we tend to do it via 24-hour composite sampling. We capture wastewater from whole communities throughout weeks and sometimes months and years. Some of our longitudinal studies are about 3 years worth in duration. It is anonymous. I mentioned it already, we don't identify individuals then. There is benefit from it too. Near real time. We are not there yet with sensing, we still need to collect samples, take them to our labs, so we call this still near real time. It is objective because it does not differentiate between different groups of people, for example, and unbiased. So the key to WB is that it is focused on people. And we've been thinking about this, that it's great to develop a tool for public health, but of course, we are environmental scientists and we always think about environmental health too. And my aim has always been to provide better linkage between public and environmental health. And this is really the way forward if we want to live in a healthier environment and we want to be healthy ourselves. So we started thinking about putting WB in the context of wider systems thinking. And you have here this One Health dimension. So One Health is a cross-sectoral, multidisciplinary effort aimed at a holistic understanding and management of public environmental health. And it is widely and successfully applied in the context of antimicrobial resistance, of AMR. We've been thinking that it works for AMR, it should work for other aspects of environmental and public health too. And we are trying to develop this tool further in the context of One Health. So what's different here? We look at whole catchments. Not only people, we look at catchments. So we look at treatment works to understand what is happening to people, but also we look at the receiving environment to understand what is the consequence for the environment. And what is important here in terms of WB in the context of One Health is that it can provide us with information about the health status of public and environment, as well as it can inform One Health actions. So certain types of interventions. Interventions can be educational in nature, it can be policy driven, and it can be technological. For example, we want to introduce new treatment process in place. So WB can help us with understanding the state of the art where we are, as well as whether the interventions that we decided to introduce were effective in nature. So very useful tool in the future. And I'm just thinking now whether Western-based biology is now water-based epidemiology, still WBE, but we are expanding to the kind of wider matrix. And of course, this is all in the context of the kind of wider exposome, not only the chemical, biological in nature, but we're also looking at other potential factors, like where we live, the kind of socioeconomics and demographics of the region we are in. And this is really the future if we want to understand our health, the drivers for our detrimental health effects, and this needs to be looked at in the context of wider issues. And this is also critical when we think about climate change that we are all facing, as well as the kind of broader aspect of sustainability. So this is very complex, and I'll just put it all together. This is how we think, so lots of different boxes. And I will just very quickly tell you what's important for us. Actually, everything here is important for us, but some things are more important than others in terms of the kind of workflows that we utilize. So, key to our work, we mainly focus on chemical markers or chemical entities in the environment. So, key to our work is mass spectrometry. And we use two types of mass spectrometry. One is the targeted one, for example, triple quadruple type of mass spectrometer, when we focus on individual chemical targets and we do the quantification of them. But we do more and more work with non-target work, when we scan through all the masses and look then retrospectively at suspects and individual chemicals. And this is captured here. Once we obtain data via our data mining approaches, we then apply them in two different ways. One is in wastewater-based epidemiology to understand community exposure assessment, and we do various different things in terms of various different workflows to undertake back calculations, to understand actual exposure. So we select various chemical residues, usually metabolites, to understand exposure, because we are after internal exposure. We are not necessarily in WB interested in how much of the chemical is out there in the wider environment. We want to know how much has gone through our bodies. That's why we focus on metabolites mainly. And actually it takes a while to verify which metabolite is fit for purpose. Sometimes for chemicals that are not intended for human consumption, there is no knowledge of metabolism. So we have to introduce various approaches. We, for example, have done human liver microsomes, S9 fraction experiments to understand how various chemicals metabolize. And once we know this, we back calculate. We take into account various different aspects like flow of wastewater, number of people in the catchment, to be able to calculate per capita exposure, per capita per day exposure, or per capita exposure per day. And we very often triangulate our data with other data sets, and you will see some examples of our work. We do triangulation with prescription of pharmaceuticals, as well as we have also done some data studies. So we want to understand how our chemical markers differ across different communities, but we also are eager to understand some of the phenomena behind in longitudinal studies. I mentioned to you already kind of 3 years worth sampling campaigns. And we also look at various different sources within catchment. So we want to see whether there is a difference between communal, industrial, and agricultural drivers within catchment. Again, I will give you some examples in a second. And we also try to tap into biological determinants. We do either ourselves, or very likely actually ask our great microbiologist colleagues that do measurements for us in terms of genetic material. So for example, bacterial or viral. And yeah, we do a little bit of modeling and epidemiology. And I will show you some examples in a second. I mentioned to you that we do studies from international, national to local scale. This is an example of our most recent national study. Various locations in England were studied, but I won't tell you a lot about it today. Actually, it's only one slide on this, and if you're interested, please feel free to look at this paper. But yeah, as promised, I will look at one particular area that we know very well, and it's called the Avon catchment. And this is the area we live in. Bath is here. And if you know the UK, you possibly have heard about Bristol. So Bristol is the largest city in this area. And why do we focus on this area? We focus on it not only because we live here, we focus on this area because we understand it very well. We work very closely with the local water utility, Wessex Water, and we get very good understanding about, for example, drivers within the catchment, the flows within the catchment, changes within the catchment, because Wessex Water obviously has an amazing oversight on what's happening in this area. So this area is about 2,000 kilometers squared, not as heavily populated. It's about 1.5 million people. And our idea years ago when we started working in this catchment was to capture as many people as possible, because we wanted to understand how people, communities really contribute to environmental burden in the catchment. And of course, as always, we had limited resource. So what we have done, we focus on 5 key towns and cities in this area. And luckily, these cities are not big enough to have more than one treatment works. So we have 5 wastewater treatment plants here. And you see them here. Town A has WWTPA, there is B, C, D, and E. So by looking at influence from these 5 different treatment works, we get an understanding of discharges from over 75% of the population in this catchment. So it's pretty amazing. We really are capturing most of the people living in the area by sampling 5 sites. We also look at the environmental burden, so before and after discharge point. This is sampling point S, 1, 2, until 8. Dark black is after discharge point. And we compare them and contrast them and want to understand what's happening. 2 of our sites, 2 of our cities have industrial presence. This region actually has very little industry. And in cities A, C, and D, there is little, if not no industry whatsoever. City B and E have higher percentage of industrial contribution, and actually City E has the highest, which is about 30% of industrial contribution. And this is the city of Bristol. And this is the catchment I will tell you a little bit about today. But before I do this, here is a list of various different targets that we look at, and it's not the final list. Actually, what you see in boxes is what we started with a few years ago. And we have various different chemicals here. We have personal care products, UV filters, some plasticizers. We have various different pharmaceuticals, from antibiotics, steroids, antifungal agents, anti-inflammatories, antidiabetics, various different agents here, through to antidepressants, antiepileptic agents, and others. We also look at pesticides, antifungal agents, veterinary pharmaceuticals. We capture lifestyle chemicals. We also tap into biology, as I mentioned earlier, especially in the context of antibiotics and AMR. We look at resistance genes. And we mine our data sets. So we every year we get more and more samples, results coming out from our retrospective data mining. So the most recent one is about antifungal agents. Yes, and we do other things too, looking at proteins as well as some viral targets too. And this is a kind of typical output from our work. This is very high level, everything pulled together in these simple pie charts. This is the catchment, as you know. In this case, we looked at 141 chemicals of emerging concern in the river catchment, and we looked at influent wastewater as well as the receiving environment. And by doing this, we obtain information within one sampling study. We obtain information about public health and environmental health. And this is critically important because you can start associating the environment with public health. Historically, we used to focus only on the environment, so we had only a fraction of the picture. Now we do so much more, and we are much more knowledgeable in terms of what needs to be done within our communities to improve our health. Very often, actually, by an improvement in environmental health. So what do we see here? This is the kind of typical pie chart representing wastewater influence. Lifestyle chemicals will be the most prevalent here. We have also anti-inflammatories, anti-diabetic drugs, mainly metformin is sitting here, as well as various other chemicals, many pharmaceuticals. And when we look at environmental samples, these pie charts are different, as you can see. This is because we have wastewater treatment in place, and various different chemicals are already removed. But we still see various different potentially hazardous chemicals, and the diabetics are still here, actually much higher percentage here than we saw in wastewater influent. And we have higher percentage of antibiotics here. Antibiotics there were very small percentage here. I can actually see them where they are here. And they are becoming much more pronounced in environmental waters, simply because they are removed as well during treatment. And this information helps us with understanding of potential environmental burden from communities, as well as we can undertake risk assessment. I won't be talking about the environmental dimension today because I'm focusing on wastewater influence, but there is so much that can be done with this data set in terms of risk assessment approaches. But what we have found out when we looked at these 5 different cities and towns is that no matter where we were, each of us individually contributed 154 milligrams per day. So this is 154 milligrams per day per person, plus minus 20 milligrams. It is interesting to realize that as communities, no matter where we are, we contribute similar chemicals because of our lifestyles. Of course, in some areas there will be more of pesticides because of our agricultural presence. In some areas there will be more industrial chemicals because of industrial presence. And of course, we sometimes suffer from different diseases, but in general, we tend to contribute per capita the same across the catchment. And I'm sure this will be different in different parts of the world. But from our regional perspective, we all individually are responsible for environmental burden in the context of household chemical usage. And we wanted to get more information about how the kind of loads of chemicals correlate with population size and what this means for us. And we did a simple association between daily loads of various different chemicals, and they are present here for you, and population size. And we did simple linear regression, and we tried to see how well the kind of correlation between daily loads of chemicals and number of people in the catchment, how well they fit in the linear model, as well as how well they correlate with each other. So we have R squared R, and we have also p-value just to show significance of this. And what we could see is that many chemicals actually correlate well. By very good correlation, I mean the darkest green that you see. Bad correlation is when you see yellow, and especially red. Okay, so this is kind of the visual help for you too. So what we could see is that certain chemicals correlate very well, and these are group 1 chemicals. These are high usage chemicals, such as anti-inflammatories, lifestyle chemicals, antiepileptics, antidiabetic. We take them all the time. These are chronic conditions. And no matter where we are, we consume per capita the same quantity. And it's very useful to know because this kind of chemicals can be used for population equivalent estimation. Now, group 2 and 3 have higher variability. Group 2, these are antibiotics and antihistamines, for example, some of the water quality indicators. Antihistamines are here. These chemicals have more seasonal usage, as well. As a result, the correlation won't be as well as significant. Group 3 is the most interesting one from a point of view of epidemiology. In this group, we have chemicals that don't correlate as well with population size. And this will be anti-cancer chemicals, this will be antihistamines, pesticides, as well as some genetic markers of resistance, and various different personal care products and industrial products. These chemicals will be more linked with cities' function, so the presence of industry or presence of agriculture. They are very useful for us in using them as early warning for potential exceedances in exposure to various different chemicals. And I'll give you some examples of this. So here we have an example of antibiotics in our catchments. Again, the same catchment, the same 5 cities. This is population size of these cities. Again, CTC is Bath, CTC is Bristol. And what we try to do here is to see whether we have correlations between antibiotics, population size. We see very nice correlation here. This is antibiotic population size. This is Pearson coefficient. The higher the number, the better. So the closest to 1, the better. Very good correlation. Now, we wanted to also see whether there is good correlation between resistance genes and population size. Correlation is not as good, but still very powerful. And we also see very good correlation between resistance genes and the antibiotic itself. So, waste-based immunology can provide us with this very interesting information about the usage of pharmaceuticals in the catchment, and we see that the higher the number of people in the catchment, the higher the usage of antibiotics. This is the same when we look at resistance genes. The higher the number of people in the catchment, the higher the number of resistance genes. And this is very interesting to see. Now, when we normalize population size, so we move from daily loads to per capita levels, we see this result plateauing. This tells us that the presence of pharmaceuticals, antibiotics in this case, as well as resistance genes in the catchment, is population size driven, more than anything else. Although you see there is a little bit of clustering happening here. Interestingly, these are 2 different regions in our larger catchment. Maybe there are different prescription patterns in these two areas. So we have Wiltshire versus Somerset. But of course, this is spatial study. 5 cities, we studied them for about a week. And we did not have really good temporal understanding of what is happening really within communities. And we were still a little bit bothered about the fact that the bigger the city, the higher the level of antibiotics as well as resistance genes. So are antibiotics really the drivers for resistance? What we did, we tried to understand this via our longitudinal study. And this is 1 year worth study when we collected samples on a weekly basis. And what you see here, a simple example, antibiotics, macrolides. Parent compound is the kind of blue color, orange color is the metabolite. And we see there is a seasonal presence of these chemicals in our catchment because of seasonal usage. Antibiotics are seasonally used. What we have done, we compared our waste of the data with prescription data. So our waste of the data are the dots, and prescription data in the catchment is the kind of the blue color. And you can see how nicely the two correlate. So the presence of antibiotics in the catchment is prescription driven. It's not always the case with all chemicals, but this is the case in this particular one. And what we have also seen is that the ratio of parent compound to metabolite is relatively stable across the board here. This indicates that we have mainly the same patterns of usage, mainly likely oral administration. But when we look at the resistance genes, they didn't really follow the same pattern. Resistance genes are these black dots. And the resistance gene that we targeted here is characteristic for macrolides, which is ERMB. And our expectation from previous slide was that if we have high usage of antibiotics, we have more resistance genes. Not the case here. And this longitudinal study allowed us to understand the simple fact that maybe antibiotics cannot be measured, the change in the antibiotics, which is very variable, cannot be a good measure for the change of resistance genes in the catchment. And then maybe there are other timescales that we need to be looking at. Once microbes get resistant, it's difficult to change this. So longitudinal studies help us in understanding this. This is another study that we've done. We looked at the changes in usage patterns of various different non-communicable disease pharmaceuticals, and in this case you have naproxen. And what we did, we looked at prescription of naproxen is pretty stable across the board, and again, this is 1 year old study. And we looked here at parent compound, which is the green color, and orange is metabolite. And you see this spike in winter time. This is a topical administration of naproxen in winter time. And we know that's topical application because we see that metabolites do not change. And why is that important? When we think about risk assessment, we always assume that pharmaceuticals are consumed in the same way. So usually orally or intravenously or topically. We do not really differentiate between the usage in different seasons. And if we don't take into account seasonal usage, we might be underestimating massively environmental impacts from naproxen in wintertime. Okay, so again, WB, this longitudinal study, gives us this really good understanding of what is happening. I have another slide on anti-inflammatories. In this case, we did look at anti-inflammatories during pandemics. So what we have here is CTA, and we have here 2 years worth study. And these grey lines indicate prevalence of COVID in communities during the study. So you can see there was a spike here, and there was another spike here. The yellow bands here, these are lockdowns in the UK. And we looked at painkillers, and you see how nicely paracetamol correlates with spikes in SARS-CoV-2. The same stands for ibuprofen, but it is not the case with naproxen as well as codeine. So you can see again, a very good analytics can give us a very good indication of what's happening in the catchment. And why am I saying this today? If we don't study SARS-CoV-2, or if there is a new viral target that we still are not aware of, how do we find out about this? We might as well test for paracetamol as a proxy for potential infectious disease happening in the catchment, viral disease happening in the catchment, because when we feel bad, we reach out for paracetamol. So it's a nice early warning proxy, potential something new happening in the community level. And we can read so much more in pharmaceutical and other chemical data sets. And I will give you just a brief example of what else we can see in this chemical fingerprints that we get from wastewater. So these are again our cities, 5 cities as we know them, and we now have broken our chemicals into groups: antidiabetics, antidepressants, cardiovasculars, illicit drugs, personal care products, industrial chemicals. And what do we see here? For example, we have very low level of antidiabetics in city C, maybe because the city has the lowest deprivation index, maybe not. It's just an idea now. I don't have any evidence at the moment to prove this, but just to give you a flavor of what pharmaceutical levels can be used for in terms of proxies for disease. Here we have large city E, with very low cardiovascular drug usage, very high illicit drug usage. You see, is observed a spike during weekend of illicit drugs. It happens across the board here. And this city has the youngest population. Maybe this is the reason for low cardiovascular drugs usage as well as high illicit drug usage. We don't know. Now, what we know is that we have high levels of various industrial chemicals in city B and C, and these two cities have high industrial presence, and we have evidence for this. Again, one fingerprint of wastewater can provide us with this rich source information about various different chemicals. And I always say sky is the limit. We target now over 200 chemicals we could, and also some viral and bacterial agents we could analyze for many more, just to provide us with a much better understanding of the community's health. I'm conscious of time, and as you have already realized, I like talking a lot, so I will try to speed up a little bit. I just wanted to tell you very briefly about how we deal with problems when we don't know which biomarker to look for. And one of our studies was bisphenol A. I'm sure you know about bisphenol A. It's regulated, banned in children's toys because it is linked with endocrine disruption actions. But it is present widely in food packaging, in paints formulations, in plastics. It's part of plastics. We wanted to understand about human exposure to bisphenol A. We have in Europe, for example, Food Safety Authority set safety standards for bisphenol A, and according to these regulations, the public that is not exposed to higher levels than the safety standards. We wanted to see whether this is really the case. But we had a problem because bisphenol A is present everywhere, so we could not use it as a biomarker. So we needed to find an approach to identify a good metabolite for it, so metabolic biomarker for us. And we have done this via retrospective data mining, as well as mentioned earlier on, a few different assays that we developed, and I should have them here. Yes, so we looked at human liver microsome and S9 fraction assay. This is just typical assays used to understand human metabolism. We also used pool urine assay and wastewater fingerprints. We pulled all this information together. We did retrospective data mining and identified bisphenol A sulfate as our metabolite. And then we mined it again in our wastewater mass spectra to get information about the chemical in question. And this is the result. So what we have seen, we have 5 cities again, and you can see the kind of the black columns indicate daily loads of bisphenol A sulfate. Of course, the higher the load, the higher exposure. You see that 3 cities, A, C, and D, these are the cities that have only a communal presence. There's no industry there. Very low exposure to bisphenol A. But city B and E have much higher exposure. And exposure happens mainly during weekdays. And we think that this might be occupational exposure linked with these industries present in these cities. And this is, I mentioned earlier on, for example, food packaging, the paint formulation. So there might be exposure to bisphenol A sulfate via this route. And I think one final example of our work is still the same piece of work, linking with parathyroid pesticide intake via food likely. So this is our bisphenol A. I've just mentioned this. You can see the spike during the weekday, during occupational exposure, lower levels during weekend, and again higher levels during weekday again. We have different situation here with parathyroid pesticides, so higher levels during weekend. Again, I don't know why this is happening. And I always say this is anecdotal, really. I don't have any evidence. Maybe it's because simply we try to eat healthy food, more vegetables during weekend. As a result, maybe we're exposing ourselves to high levels of these pesticides via food. Interestingly, some chemicals do not have any differentiation between a weekday and weekend, and this is triclosan, and triclosan is widely used as a disinfectant. So this, again, WD can be used as an early warning system for accidental chemical exposure. I could show many more examples. Oh yeah, and there is one that I want very briefly to tell you about. This is the work that we are spending a lot of time on the moment. Is actually one of the most difficult ones. Is looking at proteins to inform public health. So I'm sure you have heard about CRP. C-reactive protein is widely used to measure in our blood to identify inflammation in our body. We try to capture it in wastewater to see whether elevated levels of CRP in communities might be indicating some kind of infection. And this is the last slide putting it all together. So what we do, we started with chemical mining, we add on biological determinants because we want to understand more. We add on epidemiology data, socioeconomical and demographic data, and we move on into doing more temporal studies. They are expensive and time-consuming, but very important understanding the bigger picture. And the final slide is a big thank you to our group over years. I think this is the most recent picture, but people are changing. Some of the people that are in these photographs they have their own independent careers now, and I'm very pleased that many members of our group stayed in similar area, working, progressing this further. And I would like to thank all the funders, especially our local water utility, Wessex Water. Without them, we wouldn't be able to do this work, really. So thank you very much, and I hope I have not spoken for too long. I'm sure you have realized I'm very passionate about this topic, so I cannot stop. Thank you.
You're perfect. Thank you. Thank you very much. So Barbara has almost 150 acres in that environmental area. I think this is one of the most interesting part for me that's about your work. Like I really like how you treat the data and try to do this correlation. And before I open the for questions, I think people can be free to hand your hand to if you wanna tell the question or write in the chat. As I'm a share, I have some questions that I was intrigued because well, yesterday was the Water Day, right? World Water Day, yeah. So we discussed a little bit here about that, and then with one of to talk with one of the journalists, he said, "Do you think your water is good?" And I said, "Yes, it's good." But then can be better? Yes, can be better. Like this was the message for the day yesterday. But because in Brazil we have this particular situation about poor sanitation process. Some cities, it's very well done in this sanitation stuff, and the other ones that doesn't have any collect or treat of the sewage. So when I see this kind of data or design, experimental design, it's very interesting. But my first question is to do here in Brazil, this would be a big challenge. And then, but some questions, and then this is why I really like these data and these results from your work. My questions are little details that when I see your results, I was thinking here, look, I need to say that I'm looking at your data with our culture, right? And then maybe cannot make sense for you, but here in Brazil would be the first question. For example, when you say that in the industry, the concentrations from industries compounds are higher during the weekend, my question is, do you think that there is some input from industrial influence during the weekend on the rivers or catchment, because people don't work too much in that period, like it's less people around, or like it's more these diffuse sources that can contribute more about that? Because in Brazil it's common. Maybe it's that, oh, the industry will release the effluents during the weekend because no fiscalization or whatever.
Yeah.
Do you think this can be the reality in Italy or not?
It could be, of course it could be. So various different industries have permits to release, and actually they release the wastewater at certain times. And again, I don't know enough. It's
Yeah,
about utility, but I had discussions with them. But of course, you cannot control it as well. And to be honest, we could see the kind of release. I think it's more. I have not showed. I had no time to show you this cover result, but we could see spikes of various different chemicals here and there. They again, we were thinking pharmaceuticals mainly. We were thinking, is this linked with maybe some industrial presence, or maybe just individuals. Sorry for saying this, dumping pharmaceuticals down the drain. And the same can happen with industry. So yes, of course, you can never tell. But to be able to kind of draw these more informed conclusions from study, you need to have this longitudinal study. So 1 week worth, not good enough. For us, it was good enough to show, see, this works. But if you want to use it for legislation, for regulation, for anything else, you need to really have the longitudinal study. So test in and out and see how build the baseline. And once you have the baseline, then you see something goes up. Okay, something went up. Something happened. What has happened? Yeah. So then you do the detective work and try to understand what has happened. But yeah, without the baseline, it is difficult. And yeah, I would say it's highly likely that things can be, released during weekend, and there is no control over it.
Yeah, of course. And the other question is, you sample there are only one wastewater treatment plant per city.
Yeah.
Okay, because here we have, like, for example, Campinas has 1.2 million people, and we have 22 wastewater treatment plants. And then to do something like that, even in a small region, we also need to consider here the work day and the movement of the people, because people move from one region of the city to the center or to the downtown, for example, then during the day, the work time, and then come back to their house. So to monitor the sewage in different regions. So in your case, it's much easier to considering all of that. But this is very complex here.
Yeah. But what you need to do, and yeah, we work with bigger cities. We worked, for example, recently in the city of London, biggest city. But we targeted 2 major treatment works. One of them serves 3 million people, and the other one serves, if I remember rightly, 2 million people. So we managed to capture 5 million people within 2 treatment works. But I think user success is then to identify the best, the biggest. I guess it depends on what you're testing, isn't it? And yeah, how much results you have. Because if you have lots of results, you would just like to test it all. But if not, my recommendation always is to choose a sentinel site. So, and it is done for air quality. You have monitoring stations in various locations, the kind of critical locations. And the same is with water quality. You have monitoring stations in some parts of rivers. I would say that the same should happen for wastewater. So you choose the best places that can provide you with the most informed decision-making process down the line from the communities tested. Yeah, it is a problem, and I fully appreciate.
Yeah, and also, like, I'm trying to think about also bring this to our side. And then another question that is not so easy for us to respond when we do something similar to that here is how long the sewage takes from our houses to the wastewater. Could you have this information, like it's different from different cities or not? Or have like information about that?
So and what is happening in the sewers is critical because they're microbes in it, they're metabolized. So we need to understand this, and we do a lot of work in trying to model this. So it can be from half an hour, it can be to one whole day. It depends how big the city is, and it really is site dependent. And I always say that if you want to do this kind of thing in your place, you need to calibrate the system. You really need to understand what is happening in it, because otherwise you'll get the results, but they won't be very meaningful. And that's why I always say we do tests in various places, but our preferred one for new biomarkers is our own location because we know it so well. And it's a good one for calibration, new ideas generation, and then it can be rolled out elsewhere. But if you don't understand the city, it's difficult, really. But it's part of the process, as with everything else.
This is a good example. This is what I would say. It's a good example to think carefully about the experimental design and how to do that. Not just go there, collect the sample, bring to the lab, and then do all of the analysis, right?
Yes, exactly.
So, okay. Does someone have some questions to Barbara that want to talk to her? Yes or not? The room are full, but people are quiet here. Like in our institute, doesn't like the environmental area is not too much. Thank you, Karin.
Thank you.
I'm sure. And then I think the idea about what you do in this, like, this is to finalize. So Barbara talked a lot. I need to, right? Like, we can stay here.
We can talk forever together.
Yes. But I think this is a very interesting example to show how our lifestyles impact around us, right? The environment around us. We have different ways to show it, and ER data are very interesting and ways to explain this. And when you show this data about we contributed a lot. Like,
we do. And you know what? For me, it was interesting to see, and I always emphasize it, because whenever there is a problem with pollution, we always look elsewhere. Or there is this bad industry, or there's but someone. It's actually us. We do it. It is us, and we need to acknowledge this. And there is such a clear correlation between the number of people and pollution. It's the linear relationship in terms of what we do in our household. So, and it's a good, very good piece of information if you want to think about. So, what do we do about this? A regulation? No go, because you can regulate water utilities and make them to introduce new treatment processes. But to be honest, we've been thinking about the lifestyle changes. So maybe consuming less, which will have a huge positive effect on our environment. And some people need to hear it. Some people don't even realize that they're contributing, because it's not part of everyday thinking. So this kind of work helps with positioning, where we are as a society. Really.
This is very nice. Okay, so then, thank you, Barbara, to be with us in this afternoon, this evening for you. It's a very nice presentation and discuss. I really appreciated your effort to talk to us at that time. Thank you very much. And thank you for all to be here attending, and people that are in YouTube. So, till the next time. Thank you.
Yes, and yes, yet again, thank you very much for inviting me. It's been a pleasure.
Bye-bye.
Okay. Bye.